passion for chemistry. What I found about Josiah is when you're not looking, he's always making a joke in the lab of some type, which I caught him a couple times, which is fun for me actually, because I'm okay with making jokes in the lab at any time. So, but anyways, Josiah's going to present his research on a very similar project to Abby's, slightly different approach, and some basic elementary work to be able to sort of make any self-assembling Carsiplex. So with that, Josiah Elsberg.
So as you said, I'm Josiah Elsberg, and the title of my research, what my presentation is the chain elongation of a carceran in a self-assembling Carsiplex. So what is a Carsiplex? So a Carsiplex, as Abby might have mentioned before, is a macromolecule that encases smaller molecules. And a Carsiplex is a nice picture of an example of a Carsiplex that kind of what we're working with, similar. And consists of two carceran molecules right there, and one gas molecule. Now this gas molecule is pretty small, not very much weight in terms of molecular weight. And it also contains butane right here, which can be anything that's hydrophobic, like carbon chains or phenol groups or anything of that sort. And what a Carsiplex does inside of what the gas molecule is it creates a vacuum environment, so it makes the molecules much easier for the molecules inside to react. And the hydrophobic tails that I showed before are using hydrogen bonding and van der Waals forces to keep the gas molecule inside the Carsiplex. The only problem with Carsiplex, though, that a lot of people are working on is that once it's created, it's very difficult to remove it because it's really hard to break that bond and remove the gas molecule. So that's why we were trying to work on a reversible Carsiplex, which is a Carsiplex that has the ability to release the gas molecule much more easily. And this, as Abby pointed out, this can have many different uses, such as a chemical catalyst, like an enzyme. If you take biochemistry, enzymes do that. They take a molecule and then just release it, like that kind of exchange. Drug dispensing, you could reach a certain area and then just release it. And as well as medical imaging, just very similar to drug dispensing that use, I'm not sure if you use metal or something of that sort to do that. And not only do we want it to be reversible, but we also want it to be self-assembling. So to do this, one carceran end, as she showed before, contained an amine group, and the other one contained carboxylic acid. And we want this to form an amide, which is almost like a peptide, which is a peptide bond, and present in protein structures that we all have. So here's the general synthesis. As she pointed out, there's the 2,6-dihydroxybenzene with a group right there. X could mean anything really. And we reacted with ethanol, and we get the alcohol bowl, and then we react even further and connect those and make ether. And that's our carceran right there. So past research, they've been trying to use hydrogen bonding with carboxylic acid, and there was one issue in the synthesis where there would be a lactone rearrangement right there. So this is because if you take an organic, 6-member greens are pretty stable compared to 7-member greens, 8-member greens, things like that. So in circumstances like that, they'll just shift into that rearrangement. So the purpose of my research was to elongate the chain that the carboxylic acid was. The reason for this is actually a win-win situation because one way we would avoid lactone rearrangement because, as I said, 7-member greens and 8-member greens are not as stable, so it's much less likely for it to have it rearranged to a lactone, and it would give us a larger environment for the cavity, so we could have bigger molecules. So here is the proposed synthesis pathway. I'll just kind of go over it really quickly. We start with 2,6-dihydroxybenzoic acid right there, and then we put it in the diazomethane and diethyl ether, and we methylate ether right there. Sorry, turn it to a ester. And then we reduce that, and this isn't the same reaction. We do two separate reactions. We have anhydride or borane tetrahydrofuran, and we reduce that ester into a primary alcohol. Then we take para-thiolene sulfonic acid, that's a tough word for me to remember, and replace that alcohol with that, and then finally use potassium cyanide and an acid to make the chain longer. So the first reaction was the 2,6-dihydroxybenzoic acid and turn it into acid. And now we'll move on to the next step. And that was a successful reaction. So here's kind of the NMR. I know it's hard to see, sorry. Here's the proton NMR. And as you can see down over this area, we have the aromatic hydrogens. And which one of these is solvents. I think it's this one. This is, so I believe this was our for the ether, for the ester. But I actually relied more on the mass spec, which me and mass spec got very close together during the summertime. And as you can see, there's one nice peak right there, and the molecular weight is 168, which is the molecular weight of the compound, and the library confirmed it, the search on the library. And so, now that we have that reaction out of the way, we tried the second reaction, which would reduce that. Unfortunately, I had a little bit of an issue trying to separate the solvent and the the product. So there's a lot of THF there, and it's kind of messy, so it's really hard to read what happened. So instead of using the proton, I decided to use the mass spec again, and we got a really nice peak right there, which is good news almost, except for the fact that we have a molecule now that's 220 in terms of molecular weight, which we're not supposed to get an addition, we're supposed to subtract. So I'm not sure what happened there. We might have a product or some other thing we don't want. So we thought that the alcohols were causing the problems with the reaction. So we decided to methylate those with iodomethane. And we were successful in that. So the second reaction was performed, the second reaction again was performed the exact same way, except with a methylated alcohol instead. However, remember the mass spec of the proton, I didn't put them on here because, no, I didn't have to be slide. Anyways, basically what we got was a product that was basically this, which basically it was reducing something, but it was reducing the wrong, it was reducing the wrong sample. So the wrong, you know, sorry. Oh, I guess I did have it. Here is the product, and right there's the benzene ring, sorry, the hydrogen on the benzene, and it's a very big peak, which I'm not sure what that was, but basically I also used the mass spec for this one, and it gave us a molecular weight of 182, and a very nice peak right there, and basically that's how we kind of figured that molecule was created. So that didn't work with the aluminum hydride. We decided to use borane tetrahydrofuran, to reduce it. And unfortunately, we ran into the same issue where it was very hard to isolate the product. So again, you can see there's the aromatic range right there, aromatic hydrogens. And as for the mass spec, you got 196, which is different, but it still wasn't what we were looking for, and it was kind of hard to figure out what that molecule was. So the future of the research here is once we isolate the product and get what we want, which is a primary alcohol, we will then put it into a reaction like using para-thiolene sulfonic acid and replace it alcohol, and then again use a cyanide to add to the reaction with acid. If this is successful, we can actually add as many carbon chains as we want, so we can make it as long as we want. And then after the synthesis is done, we will test the reversibility of the carboxyplex with someone else, I believe, I think it's Dan, who has the amine, and he's working on that. And we will use 2D analog techniques, such as the DOSI, which I believe deals with the hydrogen interaction between molecules. This tests for its reversibility. So, I want to thank Dr. Nagels for putting that with me over the couple years here. Dr. Donald and Dr. Jane Cram for going through. They were the ones, as Abby said, that were the ones who kind of decided this. Henry, I think it's the Murdoch, sorry, the Murdoch Foundation. Jared Joffer, Devin Watt, Alex Behrman, and Alex Eaton, who were my predecessors to this research. And just in case you wanted to look for my sources for those pictures of the previous stuff. So, with that, are there any questions? Yes, okay.
Josiah, I mean, do you know if your stuff is clean? Is it pure?
Yeah, that's what we're trying to figure out. We've been having problems we're trying to isolate it. It's just kind of stuck in THF and stuff. And I'm having a hard time isolating it.
Did you do any kind of chromatography to?
Yes, I did, and results were. I'm not sure. I can't remember exactly what happened, but it wasn't a different product. I think I might have been reacting. I'm not sure. I kind of forget.
Because I mean, that would give you some. I mean, if your mass spec doesn't really make sense, you may have multiple things in there. Rather than,
Yeah, that's what I was thinking.
If you had multiple things in there, wouldn't the GC have shown that though?
In theory, yes, but it depends on it depends on the boiling point. Sorry. Boiling point, because it'll come off and it'll break apart. That's probably what those smaller peaks were in the mass spec. I think long peak was the size last one about it, so.
Yeah, well, I was just thinking the last one showed
Yeah, oh
something.
yeah.
But if you've got multiple, big peaks in multiple big things in there that are all fragmenting, then.
Oh yeah, I see what you mean. Yeah, that's kind of the problem with it. Yeah, it's hard to tell. It's also possible that just might be some garbage from left over from before. I guess we have to put the methanol solvent in there and see what's showing up. Compare it. Any more questions? No? All right.
Thanks.
So much better in rehearsal.
That's what I was thinking.
I did a video.
It's also kind of good. What's that? Take two. That's right. Right. Well, I was kind of sort of done.
Isn't that enough?
In isolation.
I'm gonna put a reflection on it.
I said after your
You're just standing here, you're going out.
I'm just gonna stay in here where the set up, why not?
I would like to.